Unpacking the Jevons Paradox, why increased efficiency could lead to a 30% rise in energy consumption by 2030. Date, January 30, 2025. Author, your name. Introduction. The Jevons Paradox, first articulated by economist William Stanley Jevons in 1865, presents a counterintuitive reality. As technological advancements enhance the efficiency of resource use, the overall consumption of that resource can actually increase rather than decrease. This phenomenon has significant implications for energy policy and sustainability efforts, particularly as the world moves toward ambitious climate goals. This report explores the dynamics of the Jevons Paradox, its historical context, real-world examples, the ongoing debate regarding the rebound effect, and the policy implications that arise from this paradox. Understanding the Jevons Paradox. Historical context. Jevons observed that improvements in the efficiency of steam engines led to a paradoxical increase in coal consumption. As steam engines became more efficient, coal became cheaper to use, prompting industries to utilize it more extensively. Jevons argued that enhanced efficiency does not equate to reduced consumption, rather it can lead to increased overall usage. His insights were revolutionary for their time and have been revisited in contemporary discussions on energy consumption. The mechanism of the paradox, the rebound effect. The Jevons paradox is often explained through the rebound effect. When the cost of using a resource decreases due to greater efficiency, consumers and industries are incentivized to consume more of that resource. This rebound effect can manifest in several ways. 1. Direct rebound. Lower costs lead to increased usage of the resource directly. For example, improved fuel efficiency in cars may encourage individuals to drive more miles. 2. Indirect rebound. Savings from efficiency improvements allow consumers to spend money on other goods and services which may also require energy, leading to an overall increase in consumption. 3. Economy-wide effects. As efficiency improvements stimulate economic growth, the increased overall demand can lead to higher resource consumption across the economy. Real-world examples. 1. Automotive sector. Research shows that as cars become more fuel-efficient, drivers tend to drive more, thus offsetting the potential energy savings. Electric vehicle EV owners, for instance, often report driving more than traditional vehicle owners, further highlighting the rebound effect. 2. Energy efficiency in lighting. The introduction of LED bulbs has been marketed as a way to reduce energy consumption. However, the lower cost per unit of light has led to increased use, especially during festive seasons, which has not resulted in a proportional decrease in overall energy consumption for lighting. 3. Digital technology. The efficiency gains in electronic devices have not curtailed overall energy demand. The proliferation of smart devices in data centers exemplifies how increased efficiency can lead to greater energy consumption in the tech sector. The debate on the magnitude of the rebound effect. The magnitude of the rebound effect remains a contentious topic among economists. Various classifications have emerged. Super conservation, savings exceed expectations. Zero rebound, consumption savings match efficiency gains. Partial rebound, savings are less than expected. Full rebound, no net savings occur. Backfire, overall consumption increases beyond the original level. Some studies suggest a rebound effect of around 10% in developed nations, while estimates for developing countries can exceed 50%. This disparity can be attributed to factors such as differing levels of energy accessibility, economic growth, and consumer behavior across regions. Policy implications. Re-evaluating efficiency policies. Policymakers must recognize that improved efficiency alone may not achieve desired conservation outcomes. Strategies focused solely on enhancing efficiency can be inadequate without accompanying measures to mitigate the rebound effects. Here are some potential approaches. 1. Carbon pricing. Implementing carbon taxes can help maintain energy costs even as efficiency improves. thereby discouraging excessive consumption. 2. Conservation policies. Policies that raise the costs of energy use can counteract the rebound effect. Cap-and-trade systems or stricter energy standards could help manage increased demand. 3. Public awareness and education. Raising awareness about the Jevons Paradox can empower consumers to make informed choices and foster more sustainable consumption habits. 4. Emphasizing sustainable technologies, investments in renewable energy can help mitigate the effects of rebound by reducing reliance on fossil fuels and promoting sustainable practices. Conclusion. The Jevons Paradox highlights the complex relationship between efficiency and resource consumption. While improving efficiency is essential for reducing our ecological footprint, it is crucial to recognize that such improvements can inadvertently lead to higher overall consumption. Addressing this paradox requires a multifaceted approach that combines efficiency gains with policies aimed at curbing resource consumption. By understanding the dynamics at play, stakeholders can better navigate the challenges of resource management and environmental sustainability, ultimately working toward a more sustainable future. References: 1. Jevons W. O.S. 1865. The Coal Question. 2. Saunders H. D. 1992. The Kazum-Brooks Postulate and Neoclassical Growth. The Energy Journal. 3. UK Energy Research Centre. 2007, The Rebound Effect, an assessment of the evidence for economy-wide energy savings from improved energy efficiency. 4. Wigness S., 2023. Jevons Energy Efficiency Paradox. Solar.com. 5. Wikipedia Contributors. Jevons Paradox. Wikipedia, the free encyclopedia. By understanding and addressing the Jevons Paradox, we can better align our efficiency improvements with effective sustainability practices to meet our energy consumption goals by 2030 and beyond. The Jevons Paradox presents a counterintuitive reality where improvements in efficiency can lead to increased overall resource consumption rather than the intended conservation. This phenomenon, first identified by William Stanley Jevons in the mid-19th century, showcases how enhanced resource efficiency can lower costs and subsequently encourage higher consumption levels. This paradox has significant implications for energy policy and resource management, suggesting that simply focusing on efficiency gains may not suffice for achieving sustainability goals. Counterintuitive information. 1. Efficiency leading to increased consumption. The paradox illustrates that increased efficiency in resource use does not necessarily translate to reduced consumption. For instance, when cars become more fuel efficient, the cost of driving decreases, prompting individuals to drive more, negating the intended energy savings. This rebound effect can manifest in various forms, directly, indirectly, or at a broader economic level. 2. Economic growth and resource demand. Improved efficiency often leads to lower costs, enhancing the affordability of resource use. This in turn stimulates economic growth, which can elevate overall resource demand. Therefore, the relationship between efficiency and consumption is complex, and efficiency improvements can inadvertently accelerate resource depletion rather than mitigate it. 3. Historical context. Jevons made his observations during the Industrial Revolution, when advancements like the steam engine made coal more accessible and cheaper. Consequently, overall coal consumption increased, contradicting the assumption that efficiency improvements would lead to reduced resource use. For varied rebound effects, the magnitude of the rebound effect varies across different regions and sectors. While some studies suggest a minimal rebound effect in developed countries around 10%, others indicate significant rebounds in developing nations over 50%. This discrepancy highlights the need for context-specific analyses when considering the implications of efficiency gains. 5. Policy implications. The paradox calls for a re-evaluation of sustainability strategies. Policymakers cannot rely solely on improving efficiency. They must also implement measures to manage consumption. For example, carbon taxes or other conservation policies that increase the cost of resource use can help mitigate the rebound effect. Ensuring that efficiency gains contribute to actual reductions in resource consumption. 6. Broader applicability. Beyond energy, the Jevons Paradox can apply to various resources including water and digital technologies. With the advent of more efficient technologies, the overall consumption of these resources can increase due to their lower costs, illustrating the paradox's relevance across different domains. 7. Induced demand in transportation. The concept of induced demand, commonly seen in transportation, parallels the Jevons Paradox. Just as improved fuel efficiency can lead to more driving, increased road capacity often results in more traffic as the lower costs of travel entice more people to use the roadways. 8. Technology and consumption. The rise of digital technologies serves as a contemporary example of the paradox. As devices become more efficient, their proliferation leads to increased overall energy demand. Data centers, smart devices, and other technologies often consume more energy overall despite individual efficiency improvements. Reinforcing the paradox. 9. Perception versus reality in resource use. There is a common misconception that efficiency improvements will inherently lead to conservation. This belief can result in complacency regarding resource management, as stakeholders may overlook the complexities of consumer behavior and economic dynamics that drive consumption. 10. Systemic changes required. Addressing the Jevons Paradox necessitates systemic changes in how society views resource management. Transitioning towards circular economies, promoting collaborative consumption, and integrating sustainable technologies can help break the cycle of increased consumption resulting from efficiency gains. In summary, the Jevons Paradox serves as a compelling reminder that the relationship between efficiency and consumption is complex and often counterintuitive. Simply improving resource efficiency can lead to higher overall consumption, necessitating a multifaceted approach that combines efficiency improvements with policies aimed at curbing excessive resource use. Understanding and addressing the dynamics at play is crucial for effective resource management and environmental sustainability. The Jevons Paradox presents a critical lens through which to examine the complex relationship between technological efficiency and energy consumption. While the concept itself is well known to economists and environmentalists, several nuanced aspects of the paradox are often overlooked, which can significantly impact policy decisions and sustainability efforts. Here are key points that merit deeper consideration. 1. Misinterpretation of efficiency gains. One of the fundamental misunderstandings surrounding the Jevons Paradox is the simplistic belief that increasing efficiency will automatically lead to lower consumption. This misconception arises from a lack of awareness regarding how efficiency impacts cost structures and consumer behavior. Significance: misinterpreting efficiency gains can lead policymakers to implement measures that fail to achieve their intended goals. For instance, investing heavily in energy-efficient appliances without addressing broader economic factors may not result in the expected reduction in overall energy use. Instead, it may inadvertently encourage greater consumption because the cost of using these appliances decreases. 2. Varied magnitude of rebound effects. The rebound effect, which describes the tendency for increased efficiency to lead to increased consumption, is not uniform across sectors or demographics. Factors such as income levels, existing consumption patterns, and cultural attitudes toward resource use play crucial roles in determining the extent of rebound effects. Significance: the variability in rebound effects means that blanket policies aimed at improving efficiency may not yield uniform results. For example, in wealthier nations with established consumption habits, the rebound effect may be minimal, whereas in developing countries where energy access is limited, the rebound effect could be substantial. Ignoring this variability can lead to ineffective or counterproductive policy implementations. 3. Importance of behavioral economics. The Jevons Paradox underscores the necessity of integrating behavioral economics into energy policy discussions. Traditional economic models often assume rational behavior, but in reality, consumer responses to efficiency improvements can be irrational and influenced by numerous factors, including social norms and psychological biases. Significance: by acknowledging behavioral economics, policymakers can better design interventions that account for how people actually behave rather than how they are expected to behave. For instance, educational campaigns that promote sustainable consumption habits alongside efficiency improvements may help mitigate rebound effects. 4. Historical context and lessons learned. The historical context of the Jevons Paradox offers valuable insights into its relevance today. Jevons' observations during the Industrial Revolution highlight how technological advancements can lead to unintended consequences. This historical perspective is often neglected in contemporary discussions about energy efficiency. Significance: understanding the historical precedents can help current stakeholders anticipate potential pitfalls. For instance, the rise of electric vehicles is often heralded as a solution to fuel consumption issues. However, without careful planning, the increased accessibility and affordability of electric vehicles could lead to higher overall energy consumption. Echoing the patterns seen in previous technological revolutions. 5. Economic growth and resource consumption. The relationship between economic growth and resource consumption, as illuminated by the Jevons Paradox, is particularly relevant in discussions about sustainability. Improved efficiency often leads to lower costs and increased economic activity, which can paradoxically result in higher resource consumption. Significance: this dynamic poses a challenge for policymakers who seek to decouple economic growth from resource consumption. Understanding this relationship is essential for developing policies that promote sustainable economic practices without exacerbating resource depletion. For instance, implementing a carbon tax could discourage excessive consumption while still allowing for economic growth. 6. Sector-specific considerations. Different sectors exhibit varying rebound effects and consumption patterns, which means that a one-size-fits-all approach to efficiency measures is unlikely to be effective. For example, while energy-efficient lighting may lead to increased usage in residential settings, the commercial sector might experience a different dynamic. Significance: policymakers must take a sector-specific approach to address the unique challenges and opportunities within each industry. Tailoring interventions to the characteristics of different sectors can enhance the effectiveness of energy efficiency measures and help avoid the pitfalls associated with the Jevons Paradox. 7. Technological optimism versus real-world constraints. There is often an inherent optimism regarding the potential of new technologies to address environmental issues. However, this optimism can overshadow the realities of infrastructure market readiness and consumer behavior that can limit the effectiveness of efficiency improvements. Significance: a more cautious and realistic approach to technological solutions is necessary. Policymakers should consider the broader socio-economic context and potential barriers to implementation when promoting new technologies. This perspective encourages a more holistic view of sustainability that goes beyond mere technological fixes. 8. Integration of conservation policies. The Jevons Paradox suggests that efficiency improvements should be accompanied by conservation policies that actively manage consumption levels. Policies such as carbon pricing, energy taxes, and cap-and-trade systems can help counteract the rebound effects that arise from increased efficiency. Significance: by integrating conservation policies with efficiency measures, stakeholders can create a more robust framework for sustainable resource management. This approach recognizes that efficiency alone may not suffice and that proactive measures are required to ensure that resource consumption does not spiral out of control. 9. Public perception and education. Public understanding of the Jevons Paradox and its implications is often limited. Many consumers lack awareness of how their behavior may contribute to increased consumption even when using supposedly energy-efficient technologies. Significance: Raising awareness about the complexities of the Jevons paradox can empower consumers to make more informed choices about their energy use. Educational initiatives that highlight the interplay between efficiency and consumption can foster a culture of sustainability that goes beyond superficial compliance with efficiency standards. 10. The future of sustainability initiatives. As we look toward the future, the lessons learned from the Jevons paradox will be crucial in shaping sustainable practices and policies. With the anticipated increase in energy consumption by 2030 largely driven by efficiency improvements, it is imperative to adopt a more comprehensive approach that balances efficiency gains with responsible consumption. Significance. The future of sustainability initiatives hinges on our ability to navigate the complexities of efficiency and consumption. By understanding the nuances of the Jevons paradox, stakeholders can better design policies that not only promote efficiency but also actively manage consumption patterns to achieve true sustainability. In summary, while the Jevons paradox serves as a warning about the complexities of efficiency and consumption, it also offers a roadmap for developing more effective sustainability policies. By recognizing the overlooked aspects of this paradox and integrating them into policy discussions, we can work toward a more sustainable future that genuinely reduces resource consumption rather than inadvertently increasing it. 1. Understanding the Jevons paradox and the rebound effect. The Jevons paradox encapsulates the phenomenon where improvements in resource efficiency can lead to an increase in overall consumption, countering the expected conservation benefits. This is primarily due to the rebound effect, which manifests as consumers take advantage of lower costs associated with more efficient technologies. The rebound effect is categorized into various degrees, from zero rebound, where efficiency gains are fully offset by increased consumption, to backfire, where consumption exceeds initial levels. Understanding this paradox is crucial for policymakers and economists, as it challenges the assumption that efficiency improvements alone will lead to reduced resource consumption. 2. Real-world examples of the paradox. Several sectors exemplify the Jevons paradox, showcasing its implications in practical applications. Automotive sector. Increased fuel efficiency often leads to higher mileage driven. Studies indicate that electric vehicle users tend to drive more than their gasoline counterparts, thus negating some of the energy savings. Energy efficiency in lighting. The adoption of LED technology, while reducing the energy needed per unit of light, has not necessarily decreased total energy consumption for lighting. Instead, lower costs have encouraged more extensive use, particularly for decorations during festive seasons. Digital technology consumption. Despite advances in the efficiency of electronic devices, the demand for energy has surged with the proliferation of smart technologies in data centers, illustrating how increased efficiency can lead to higher overall energy demand. 3. Debate on the magnitude of the rebound effect. There is significant discourse among economists regarding the magnitude of the rebound effect. While some studies suggest minimal rebound in developed nations, others argue that developing countries could experience substantial rebounds due to increased energy accessibility. Historical assessments such as those by the UK Energy Research Centre suggest that rebounds may range from 10% in developed countries to over 50% in developing countries. This debate is critical as it influences how strategies for energy efficiency and sustainability are formulated and implemented. For policy implications and recommendations, the Jevons paradox has profound implications for policy formulation. Simply enhancing efficiency without considering consumption patterns may not achieve sustainability goals. Policymakers are encouraged to adopt multifaceted approaches that combine efficiency improvements with measures to mitigate rebound effects, such as implementing carbon taxes or conservation policies that raise the cost of energy use. Such strategies may help curtail excessive consumption and ensure that efficiency gains contribute to actual resource conservation rather than inadvertently promoting increased use. In conclusion, the Jevons paradox highlights the complexity of the relationship between efficiency and consumption, emphasizing the need for comprehensive strategies to navigate the challenges of resource management and environmental sustainability. Understanding this phenomenon and its implications is essential for creating effective policies that truly lead to reduced resource consumption and enhanced sustainability. 1. The agricultural efficiency paradox. The Green Revolution, which began in the mid-20th century, introduced high-yield crop varieties, chemical fertilizers, and advanced irrigation techniques to increase food production significantly. While these innovations made it possible to produce more food with less land, they also led to increased agricultural land use as farmers expanded their cultivation areas to capitalize on the higher yields. Consequently, instead of reducing the overall land required for agriculture, the Green Revolution contributed to deforestation and habitat loss as more land was converted for farming. 2. The induced demand in transportation. The phenomenon of induced demand is often observed in transportation infrastructure. When road capacity is increased, such as through the construction of new highways or the addition of lanes to existing roads, traffic congestion initially decreases. However, this reduction in congestion often leads to increased travel as people feel encouraged to drive more due to the improved conditions. Over time, this can result in traffic levels returning to or exceeding previous congestion levels, effectively negating the intended benefits of the infrastructure improvements. This mirrors the Jevons Paradox, where efficiency leads to increased overall use. 3. The water efficiency paradox. The construction of large reservoirs and the implementation of water-saving technologies can sometimes lead to increased water consumption rather than conservation. As water becomes more readily available and affordable due to these improvements, consumers may increase their usage for agricultural, industrial, or recreational purposes. This situation was highlighted in studies of regions where enhanced irrigation systems led to higher agricultural yields, prompting farmers to cultivate more land and use larger quantities of water, ultimately leading to increased overall water consumption despite the initial goal of conservation. Future outlook. Unpacking the Jevons Paradox and its potential impact on energy consumption by 2030. The Jevons Paradox, which suggests that improvements in energy efficiency can lead to increased overall consumption of energy, poses significant implications for future energy policies and consumption trends. As we look toward 2030, the paradox may become increasingly relevant, potentially leading to an estimated 30% rise in global energy consumption. This projection stems from a combination of technological advancements, economic growth, and behavioral responses to energy efficiency improvements. 1. Technological advancements and their implications. The ongoing development of energy-efficient technologies will continue to transform various sectors, including transportation, manufacturing, and residential energy use. As electric vehicles, EVs, and smart appliances become more prevalent, the cost of energy consumption will decrease. Lower operational costs can encourage consumers to adopt these technologies at a larger scale, thereby increasing energy use rather than decreasing it. For instance, the widespread adoption of EVs, which are often more efficient than traditional gasoline vehicles, has been linked to increased travel distances among drivers, directly illustrating the rebound effect. 2. Economic growth and energy demand. Global economic growth is projected to continue, especially in developing countries where access to energy is expanding rapidly. As economies grow, so does the demand for energy-intensive goods and services. The rebound effect will be magnified in these regions as increased access to affordable energy allows for higher consumption. The International Energy Agency (IEA) anticipates that emerging markets will drive a significant portion of the increase in global energy demand, contributing to the potential rise in consumption in the coming years. 3. Behavioral responses and consumption patterns. Consumer behavior plays a crucial role in determining the magnitude of the rebound effect. The tendency for consumers to take advantage of reduced costs associated with greater energy efficiency can lead to increased overall consumption. For example, as home heating and cooling systems become more efficient, homeowners may choose to maintain more comfortable temperatures year-round, ultimately using more energy. Additionally, the advent of smart home technologies can create a false sense of security regarding energy consumption, as users may not fully recognize the implications of increased usage. 4. Policy implications and strategic responses. Recognizing the potential for the Jevons paradox to undermine energy efficiency gains, policymakers must adopt a multifaceted approach to energy management. Relying solely on efficiency improvements without complementary measures could lead to unintended consequences. Effective solutions may include implementing carbon pricing. A carbon tax could be an effective mechanism to maintain energy costs despite improvements in efficiency. By increasing the economic burden of energy consumption, it may discourage excessive usage and promote conservation. Encouraging sustainable behaviors. Policies that promote energy literacy and awareness about the Jevons paradox can help consumers make informed decisions. Programs designed to educate the public on sustainable energy consumption can mitigate the rebound effect. Investing in renewable energy. Transitioning to renewable energy sources can help counteract the rebound effect by decoupling energy consumption from fossil fuel use. As renewable energy becomes more affordable and accessible, it can potentially reduce the overall environmental impact while accommodating increased demand. 5. The future consumption landscape. By 2030, the combination of efficiency improvements, economic growth, and behavioral changes may result in a 30% rise in global energy consumption. This increase will challenge existing sustainability goals and necessitate innovative policy responses. Countries must balance the pursuit of energy efficiency with strategies that address the complex dynamics of consumption patterns and the rebound effect. In conclusion, the Jevons paradox serves as a cautionary tale for policymakers and energy stakeholders. As we advance toward 2030, understanding the intricate relationship between efficiency and consumption will be vital in shaping a sustainable energy future. The challenge lies not only in improving efficiency but also in implementing strategies that effectively manage and mitigate increased consumption, ensuring that sustainability efforts are not undermined by unintended consequences.